A faint whisper of radiation fills the entire cosmos. This is the cosmic microwave background, the oldest light in the universe, and it holds secrets that keep scientists awake at night. By the end of this journey, you will understand why this ancient glow challenges everything we think we know about reality. We will uncover why distant parts of the universe are mysteriously synchronized and explore the startling evidence for a multiverse. What does it feel like to confront a puzzle that could rewrite the laws of physics? Two young astronomers named Arno Penzias and Robert Wilson were troubleshooting a peculiar noise in 1965. Their massive horn antenna in New Jersey picked up a persistent, faint hiss that came from every direction, day and night. They scrubbed the antenna clean of pigeon droppings, but the signal remained, an unshakable whisper from the cosmos itself. They had accidentally stumbled upon the oldest light in the universe. This was the cosmic microwave background, the cooled and stretched remnant of the universe's fiery birth. Think of the entire cosmos, once unimaginably hot and dense, expanding and cooling over billions of years. The light from that initial inferno has been traveling ever since, its energy fading until it now reaches us as a faint microwave glow, bathing the entire universe in a nearly uniform temperature of 2.7 degrees above absolute zero. This moment of release happened when the universe was about 380,000 years old. Before that, it was a searing, opaque fog of plasma, where light was constantly trapped, bouncing between particles. As the universe expanded and cooled, protons and electrons finally combined to form the first neutral atoms. Suddenly, the fog cleared. Photons, the particles of light, were set free on a journey across spacetime. This ancient afterglow is the ultimate confirmation of the Big Bang, a baby picture of the cosmos. But this picture holds a profound secret. Its near-perfect uniformity is itself the very thing that creates a monumental puzzle. Why does the entire universe look so eerily similar, as if every part had once been in touch with every other? That near-perfect uniformity is the source of a deep and troubling cosmic mystery. Look at any two distant spots on the cosmic microwave background map, regions on opposite sides of the sky. According to the standard story of the Big Bang, these two places are so far apart that light, traveling at the universe's ultimate speed limit, has not had nearly enough time to journey from one to the other since the cosmos began. They exist beyond each other's cosmic horizons, forever out of touch. Yet, when we measure them, they share the exact same temperature to an astonishing precision. It is as if two people living in completely isolated towns, with no means of communication, decided to paint their houses the exact same shade of blue at the exact same moment. This is the horizon problem, and it suggests that these distant parts of the universe were somehow in contact long ago. To solve this, scientists proposed a breathtaking idea, a cosmic plot twist called inflation. The theory suggests that in the very first fraction of a second of its existence, the universe underwent a growth spurt of unimaginable ferocity. It expanded faster than the speed of light, stretching a single, tiny, connected patch of spacetime into the entirety of our observable cosmos. This violent, exponential inflation smoothed everything out, ironing the wrinkles from reality and setting the same temperature everywhere before the standard, slower expansion of the Big Bang even began. It is an elegant and powerful solution, explaining the uniformity we see with a single, dramatic event. Yet, like any good mystery, this elegant answer only opens the door to a much deeper enigma. What force could possibly be powerful enough to wrench spacetime itself apart in such a violent, explosive moment? The search for that engine of creation pushes our understanding of physics to its absolute breaking point, forcing us to confront the most fundamental laws that govern existence itself. That force, the engine of cosmic inflation, is perhaps the greatest unknown in all of modern physics. Scientists call it the Inflaton field. Picture a ghostly, invisible energy field that saturated every point of the infant universe. For a fleeting sliver of time, this field was the dominant power in existence, and it possessed a bizarre property. It generated a form of repulsive gravity. Instead of pulling things together, this force violently pushed space itself apart, accelerating the expansion to speeds beyond comprehension. This was not an explosion in space, but an explosion of space, stretching a subatomic speck into a macroscopic cosmos in less than a billionth of a billionth of a billionth of a second. But what is this Inflaton field, really? The truth is, we have no idea. The name Inflaton is merely a placeholder in our equations, a label for a ghost in the cosmic machine. We see the effects of its work in the stunning uniformity of the cosmic microwave background, but the particle associated with this field, the Inflaton particle, remains entirely hypothetical. It has never been detected, and its fundamental properties are a complete mystery. This is why the hunt is so urgent. Different theoretical models of inflation predict different behaviors for this field, and each behavior would have left a unique fingerprint on the ancient light of the cosmic microwave background. The most promising place to look for this fingerprint is in the polarization of that light, a specific pattern in the way its waves are oriented. Sophisticated experiments at the South Pole and in high-altitude balloons are scanning the sky, desperately searching for this faint primordial signal. Finding it would be like discovering the signature of the universe's architect. The continued elusiveness of the Inflaton is a primary reason the cosmic microwave background is not a solved puzzle, but an active, urgent frontier. It pushes us to ask what other fundamental forces were at play in that first moment, and whether we are even equipped to understand them. Yet, this is not the only shadow that falls across this ancient light. The very mechanism of inflation, this breathtaking solution to one cosmic riddle, may have opened the door to a concept so vast it challenges our place in reality itself. But as we peer into this ancient light, another peculiar detail emerges, one that challenges our understanding of the universe on its grandest scales. When scientists create a temperature map of the cosmic microwave background, they break it down into patterns, much like a musician separates a complex chord into its individual notes. These patterns are called multipoles. The most significant of these, after the overall uniform temperature, is the quadrupole moment. It represents the most fundamental, large-scale wrinkles in the fabric of the early universe, the broadest strokes on the cosmic canvas. According to our most trusted models of cosmic evolution, this quadrupole moment should be relatively strong, a clear and distinct note in the symphony of creation. Yet, when we measure it with exquisitely sensitive instruments like the Planck satellite, we find something deeply puzzling. The quadrupole is strangely faint, almost muted. It is as if you were listening to a grand orchestra and discovered that the cellos, the foundation of the entire piece, were playing at a whisper. The sound is there, but it lacks the power and presence that the composer's score demands. This is the curious case of the missing quadrupole. Could this simply be a statistical fluke, a cosmic coincidence in the data we have collected? The probability is low, which leads scientists to consider more profound possibilities. One compelling idea is that the universe may have a non-trivial topology. In simple terms, our cosmos might not be infinite and flat in the way we typically imagine. It could be folded in on itself in a complex shape, like a video game where going off one edge of the screen brings you back to the other. If the universe is structured this way, its finite size could actually suppress the largest possible waves, explaining why we see a weaker quadrupole than expected. Another, even more mind-bending explanation is that what we call the observable universe is merely a finite patch within a vastly larger, perhaps infinite, whole. The patterns we see are just local statistics, and the true grandeur of the cosmos on its ultimate scale is hidden from our view. This anomaly is a powerful, humbling reminder. Our best models of the universe, for all their predictive power, are still incomplete. The largest scales we can observe may be whispering secrets that our current theories are not yet equipped to hear, pushing us to look closer, to examine the cosmic microwave background with even greater precision. And when we do, we find that its smoothness is only an illusion, a veil over a hidden world of intricate structure. Yet even this strange quiet on the largest scales is not the final oddity. A far more unsettling pattern emerges when we examine the very direction of these cosmic wrinkles. The largest features in the cosmic microwave background, the so-called low multipoles, show a bizarre and deeply troubling alignment. Their planes, the axes along which they are oriented, are not randomly scattered across the sky as our most fundamental principles demand. Instead, they appear to line up with one another, creating a kind of cosmic spine in the heavens. Even more shocking, this preferred direction, this axis, also seems to align with the plane of our own solar system. Scientists, with a mix of dread and dark humor, have named this the axis of evil. The name is not an exaggeration. It strikes at the very heart of modern cosmology, a field built upon the cosmological principle. This principle states that the universe on large scales is isotropic and homogeneous. There are no special places and no special directions. The universe should look roughly the same from every vantage point. The axis of evil suggests we might be living in a universe with a preferred direction, a fundamental lopsidedness, and worse still, that our own insignificant corner of it seems to be weirdly aligned with this cosmic architecture. The debate this has sparked is fierce and unresolved. Could this simply be a flaw in how we process the data from our telescopes, a subtle systematic error that has crept into our measurements? Perhaps it is a local effect caused by dust or other foreground material within our own Milky Way galaxy that we have not fully accounted for. Or, in the most unsettling scenario, is this alignment a genuine feature of the universe, a crack in the foundation of our standard model? If this axis is real, it forces us to confront the terrifying possibility that we do, in fact, occupy a special place, a notion science has fought to reject for centuries. It is a mystery that forces cosmologists to question everything, from their data to their most cherished assumptions, all while searching this ancient light for the faint seeds from which every galaxy, star, and planet would eventually grow. These faint temperature ripples, these 1 part in 100,000 imperfections, are the most important structures in the entire cosmos. They are the primordial seeds from which every galaxy, star, and planet eventually grew. Without these tiny variations, this subtle lumpiness in the early universe, matter would have remained perfectly smooth, and the cosmos would be a vast, dark, and empty sea of featureless gas. We would not exist to ponder it, so what was the original sculptor of these cosmic seeds? The answer may lie in the most counterintuitive realm of physics, the quantum world. During that explosive inflationary period, the universe was subatomic in size. At such a minute scale, the rules of quantum mechanics reigned supreme. Empty space was not truly empty, but a seething, bubbling foam of virtual particles, constantly flickering in and out of existence. These are quantum fluctuations, temporary borrowings of energy that defy our classical intuition. the Inflaton field itself was subject to these tiny, random jitters. As the universe underwent its fantastically rapid expansion, these microscopic quantum fluctuations in the field were stretched exponentially, frozen into the fabric of spacetime itself. A region with a slightly higher density of Inflaton energy would expand just a bit differently than a region with slightly lower energy. These minute differences became the blueprint for all future structure, imprinted as the temperature variations we now see in the cosmic microwave background. It is a staggering concept. The grand cosmic web of galaxies, with its vast clusters and empty voids, can trace its origin back to quantum jitters, to vibrations smaller than an atom, magnified to a cosmic scale by inflation. Yet this elegant story contains a profound gap in our understanding. How exactly do these quantum probabilities, these mere possibilities, become the concrete, classical reality of a temperature map? The transition from the fuzzy, probabilistic quantum world to the definite, measured classical world is one of the deepest puzzles in all of physics. The cosmic microwave background presents us with the ultimate evidence that this transition happened, but we still do not know how. This ancient light does not just show us the universe's baby picture, it ties the fate of everything we see to the bizarre, foundational rules of quantum mechanics, leaving us to wonder if we are seeing the ghost in the machine of creation itself. This hunt for quantum ghosts leads to one of the most profound chases in all of science, the search for primordial gravitational waves. These are not waves in water or air, but ripples in the very fabric of spacetime itself, theorized to have been generated by the violent tremors of cosmic inflation. If the quantum fluctuations are the seeds of matter, these gravitational waves would be the echo of space itself being wrenched apart. Their predicted signature is a specific, curling pattern frozen into the polarization of the cosmic microwave background, a fingerprint known as B-mode polarization. Finding this faint swirl would be like hearing the universe's first cry. The excitement reached a fever pitch in 2014 when the BICEP-2 collaboration, a team using a telescope at the South Pole, announced they had detected this very signal. It was a monumental moment, hailed as a direct glimpse into the Big Bang, but the celebration was short-lived. Further analysis, crucially incorporating data from the Planck satellite, revealed a heartbreaking truth. The signal they saw was largely, if not entirely, contamination from interstellar dust within our own Milky Way galaxy. The faint whisper they thought was from the dawn of time was just cosmic dust motes casting a shadow. This disappointment, however, did not end the hunt. It refined it. The search for these primordial waves is now a monumental, global effort involving ever more sensitive telescopes at the South Pole, in the high Chilean deserts, and on balloons soaring above the thickest parts of our atmosphere. The stakes could not be higher. Detecting these waves would not only confirm inflation, but would allow us to probe the universe at energy scales 1 trillion times higher than anything achievable at the Large Hadron Collider. We would be testing physics at the moment of creation itself. Their continued absence is not a failure, but a guide. It forces scientists to constantly refine their models and their instruments, forever wondering if the universe's most cataclysmic event left behind only the faintest of traces, a whisper we are still learning how to hear. Even as we chase these echoes of creation, a more immediate and unsettling conflict has emerged, one that measures the very pulse of the cosmos and finds two contradictory heartbeats. This is the crisis of the Hubble constant, the number that describes how fast the universe is expanding today. To understand the problem, we must look at two different clocks. The first clock is built from the ancient light of the cosmic microwave background. By studying the precise patterns in that baby picture, scientists can wind the cosmic film backward, following the physics of the early universe forward in time to predict what the expansion rate should be right now. It is a forecast based on our most fundamental understanding of cosmic history. The second clock is built from modern observations. Astronomers use stars called Cepheids variables and cataclysmic supernova explosions as standard candles, celestial lighthouses of known brightness. By measuring how much dimmer these objects appear to us, they can directly calculate their distance and, in turn, measure the universe's current expansion rate directly. Both methods are incredibly sophisticated, refined over decades, and pursued by brilliant, careful teams, and they give two different, stubbornly persistent answers. The universe today, according to local measurements, appears to be expanding faster than the early universe's physics says it should be. This discrepancy is not a small statistical wiggle. It is a gap that has only widened with better data and more precise instruments. Scientists call this the Hubble tension, a polite name for what could be a full-blown crisis in cosmology. Think of it like this: you have two separate, trusted maps telling you how to get to the same destination. One map, based on the starting point and the known rules of the road, says your journey should take exactly 1 hour. The other map, using real-time GPS data from your car, insists you are driving much faster and will arrive in just 50 minutes. Both cannot be correct. Something is wrong with your understanding of the journey, the car, or the very road itself. The implications of this tension are profound. It could mean there is a hidden ingredient in our cosmic recipe, a new type of dark energy that briefly surged in the universe's adolescence, giving expansion an extra kick. Perhaps an unknown species of subatomic particle was flooding the early cosmos, subtly altering how it evolved. Or, in the most unsettling scenario, our foundational model of the universe, known as lambda CDM, which has beautifully explained so much, is simply incomplete, missing a crucial piece of physics that we have not yet even conceived. This is not a minor puzzle for specialists to tidy up. It is a direct challenge, a signal that the universe is still holding back its deepest secrets, forcing us to question whether we truly understand the engine of cosmic expansion that has shaped everything we see. This fundamental gap between the universe's expansion history and its present speed is not the only profound question the cosmic microwave background leaves unanswered. The ancient light holds another, even deeper secret, one concerning the very substance of the cosmos. We can see the stars and galaxies, the planets and the gas clouds, but all of that, everything made of atoms, represents less than 1/6 of the total matter in the universe. The rest is a complete mystery, a ghost that permeates space, invisible and untouchable. This is the puzzle of dark matter. We know it is there because of its immense gravitational pull. It is the hidden scaffolding upon which the cosmic web of galaxies is built, the force that keeps stars from flying out of their galactic homes, and the cosmic microwave background provides our most compelling evidence for its existence and its quantity. How can a picture of ancient light reveal something that is completely dark? It works because dark matter, while invisible to light, has a powerful gravitational influence. In the hot, dense plasma of the early universe, normal matter, the protons and electrons that make up everything we see, was constantly pushed and pulled by the pressure of light. Dark matter, however, was aloof. It did not feel this pressure as it only interacts through gravity. This difference in behavior left a distinct fingerprint on the primordial plasma. The gravity from clumps of dark matter acted as anchors, creating gravitational wells that attracted the surrounding soup of normal matter and light. The precise patterns of hot and cold spots we see in the cosmic microwave background, the specific sizes and distribution of those anisotropies, are a direct record of this ancient tug of war. By measuring these patterns with exquisite care, cosmologists can run the cosmic film backward and measure the total amount of matter present in the early universe. The answer they get is staggering. The data from the Planck satellite and other observatories tell us that dark matter makes up roughly 85% of all the matter that exists. The cosmic microwave background tells us with remarkable certainty that dark matter exists and exactly how much of it there is, but here the ancient light falls silent. It reveals the ghost shadow, its weight and its influence, but it cannot tell us the ghost's name. The specific particle nature of dark matter remains entirely hidden within the subtle statistics of the primordial glow. Is it a vast cloud of exotic, slow-moving particles, a concept known as WIMP? Or is it something even stranger, like a universe-spanning field of ultralight particles? The CMB gives us the most important clues of all, the what and the how much, but the final piece of the puzzle, the ultimate identity of this substance that shapes the cosmos, is a mystery that still compels a desperate, global search in deep underground laboratories and powerful particle colliders, all hoping to catch a glimpse of the universe's dominant material. But the shadow of dark matter is only half the story of the missing universe. An even more elusive force is at work, one that the cosmic microwave background reveals in a startlingly indirect way. This is the enigma of dark energy. We have known since the late 1990s that the universe is not just expanding, but its expansion is accelerating, as if space itself were being stretched apart by some invisible, repulsive force. The cosmic microwave background provides our most powerful evidence for this bizarre component. How can a snapshot of the infant universe tell us about the expansion rate today? It works because the CMB gives us a precise measurement of the universe's geometry. The patterns of hot and cold spots, their specific sizes, act as a standard ruler. By seeing how these rulers appear bent or magnified by the gravitational lensing of intervening matter, scientists can trace the entire expansion history of the cosmos, from its first moments to the present day. The data delivers a clear and humbling verdict. Ordinary matter and dark matter together make up only about 31% of the total energy budget of the universe. The remaining 69% must be this mysterious dark energy, the fuel for cosmic acceleration. The CMB confirms its overwhelming presence and its dominance in the cosmic ledger. Yet for all its power, the ancient light cannot tell us what dark energy actually is. The simplest idea is that it is a cosmological constant, an unchanging energy intrinsic to the vacuum of space itself. This was an idea Albert Einstein first proposed and then discarded, but the CMB data, when combined with other measurements, cannot yet rule out more exotic possibilities. Perhaps dark energy is not constant at all. It could be a dynamic field dubbed quintessence that evolves over time, its strength waxing or waning. It might even be a sign that our theory of gravity, Einstein's general relativity, breaks down on the largest cosmic scales. The CMB sets the stage for this profound mystery, confirming the actor is there but keeping its identity completely hidden behind the curtain. It points the way for a new generation of telescopes and space missions, designed to measure the universe's expansion over the last several billion years with exquisite precision, hoping to catch dark energy in the act of changing, or to confirm its eerie, constant nature. This is arguably the greatest puzzle in all of physics, and the cosmic microwave background, our oldest and most trusted map, tells us we have only just begun to read it. This ancient light provides perhaps the most fundamental measurement of all, the very shape of space itself. The patterns in the cosmic microwave background act as a cosmic tape measure, allowing scientists to perform a remarkable feat of geometry on the grandest possible scale. They are testing whether the universe is flat, like an infinite sheet of paper, or curved, like the surface of a sphere or a saddle. The results from missions like Planck are startlingly precise. The data tells us that the universe is geometrically flat to within a razor-thin margin of error. In the language of general relativity, this flatness is not an accident. It corresponds to a specific critical density of matter and energy in the cosmos, a perfect balance where the expansion energy exactly counteracts the pull of gravity. This is the universe's ultimate balancing act. But is this flatness perfect, or is it merely a very, very close approximation? A perfectly flat universe is a theoretically fine-tuned condition, one that seems almost too perfect to be true. Imagine balancing a pencil perfectly on its tip for billions of years. The slightest breath of wind, the tiniest vibration, would send it toppling. The universe's flatness presents a similar puzzle. For it to be so exquisitely flat today, its density in the first moments of the Big Bang must have been fine-tuned to an unimaginable precision, to within 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. This level of perfection defies belief, and it is one of the primary reasons the theory of inflation was so welcomed. The violent, exponential stretching of space during inflation would have forced the universe toward this flat state, much like how blowing up a gigantic balloon makes its surface appear flatter and flatter from our local perspective. Yet the question remains, is the flatness absolute? Even a minuscule, undetectable curvature would have profound implications. A positively curved universe would eventually stop expanding and collapse in a big crunch. A negatively curved one would expand forever into ever-increasing emptiness. A truly flat universe sits on the knife edge between these two fates, destined for a slow, cold end. The quest to measure this curvature with even greater precision is a driving force in cosmology, because a definitive answer would place powerful constraints on the very models of inflation that supposedly created this flatness in the first place. It forces us to ask if we are seeing the true, infinite geometry of everything, or merely the local flatness of our own observable patch within a far grander and potentially curved cosmic whole. The universe's first few minutes were a forge for the simplest atoms, a process we call Big Bang nucleosynthesis. This brief, searing epoch produced the primordial hydrogen and helium that would later fuel the first stars, and our models for this cosmic alchemy are spectacularly successful. The amounts of deuterium and helium we observe in the oldest corners of space match the theoretical predictions with stunning accuracy. It is a triumph of modern cosmology, a confirmation that we understand the basic physics of the universe's fiery youth. Yet there is one stubborn, glaring exception, an anomaly that stands out like a single wrong note in an otherwise perfect symphony: the element lithium. According to our most trusted calculations, the Big Bang should have left behind a specific, measurable amount of lithium-7, the most common isotope of this light metal. But when astronomers look at the oldest stars in our galaxy, the pristine relics from the early cosmos, they find only about a third of the predicted lithium. The universe is missing its lithium. This is not a small statistical error. It is a factor of 3 discrepancy, a gap that has persisted for decades despite increasingly precise observations and refined theories. Since the initial conditions for Big Bang nucleosynthesis are set by the physics we measure from the cosmic microwave background, this lithium problem points directly to a crack in our model. The CMB gives us the temperature, density, and expansion rate of the early universe, the very recipe for elemental cooking. The fact that the helium and deuterium come out perfectly, but the lithium does not, suggests something subtle and profound is missing from our understanding of that first nuclear forge. What could have consumed the lithium or prevented it from forming in the expected amounts? The possibilities are as fascinating as they are elusive. Perhaps an unknown, exotic particle was present in those first moments, a relic that interacted with nuclei and altered the delicate chain of nuclear reactions. Maybe there was a decay process we have not yet considered, where a hypothetical particle decayed and dumped extra energy into the primordial soup, breaking apart the fragile lithium nuclei as fast as they formed. Or, in a more radical twist, could our understanding of nuclear physics itself be incomplete under the extreme, universe-spanning conditions of that first forge? This puzzle connects the grandest scales of cosmology, as revealed by the ancient microwave light, to the very chemical building blocks that would one day form planets and life. It is a humbling reminder that even the simplest atoms can hold profound secrets, and that our cosmic baby picture, for all its clarity, still hints at a hidden chapter in the story of creation. Scattered across the southern sky lies a blemish on the cosmic baby picture, a region of cold so pronounced it defies easy explanation. This is the cold spot, an area in the cosmic microwave background significantly cooler than its surroundings, stretching over 1 billion light-years. One leading theory paints a picture of a cosmic desert, a supervoid of staggering proportions. As light from the CMB travels through such an underdense region, it must climb out of a gravitational well. But in an accelerating universe dominated by dark energy, the well itself is becoming shallower as the void expands. The light, having expended energy to enter the void, does not get all of that energy back as it leaves, causing a net loss that we observe as a cold spot in the ancient glow. This is the integrated Sachs-Wolf effect, a subtle but real imprint of large-scale structure on the primordial light. Yet the puzzle deepens. Surveys mapping the distribution of galaxies suggest that while there is a void in the general direction of the cold spot, it may not be vast or empty enough to account for the dramatic temperature drop we see. The effect is like expecting a deep, steep crater to explain a sudden chill, but finding only a gently sloping depression. This mismatch has forced cosmologists to consider possibilities far more radical. Could the cold spot be a bruise on our cosmos, the imprint of a collision with another universe in the vast multiverse? In such a scenario, the cosmic inflation that birthed our universe may have been just one bubble among many in a frothing, eternal meta-universe. If two such bubbles grazed each other in the earliest moments, the energy released at their boundary could have left a permanent, cooler scar on the CMB of our own bubble. It is a breathtaking proposition that we might be seeing evidence for a reality beyond our own imprinted on the oldest light we can see. Whether it is a statistical fluke, an unusual but natural supervoid, or a window into the multiverse, the cold spot remains a stubborn imperfection, a quiet reminder that our most detailed map of the cosmos still contains regions labeled "Here be dragons." This ancient light reaches us only after an epic journey, filtered through the cosmic neighborhood of our own Milky Way. The pristine signal of the cosmic microwave background is not what our telescopes detect first. Instead, they capture a cacophony of foreground emissions, a fog of local interference that scientists must painstakingly peel away to reveal the true primordial whisper. Our galaxy glows with its own light, which masks the CMB in three primary ways. The first is synchrotron radiation, a ghostly glow generated by high-energy electrons spiraling at nearly the speed of light through the Milky Way's vast magnetic fields. The second is thermal emission from cosmic dust, tiny grains warmed by starlight that re-radiate that energy and create a pervasive, dusty haze. The third is free emission, a faint radio hiss produced when free electrons and ions in hot, ionized gas briefly interact and then fly apart. Each of these foregrounds shines with a different spectral signature, a unique color that changes with the frequency of observation. To separate them, cosmologists use telescopes that observe the sky at many different frequencies simultaneously, building a kind of cosmic fingerprint database. They create intricate models of our galaxy's emissions, and then, like a master art restorer cleaning centuries of grime from a priceless painting, they digitally subtract these foregrounds from the total signal. The goal is to leave behind only the pure, unadulterated light from the dawn of time. But this is where the danger lies. Any error in this complex cleaning process, any misjudgment in the model, can have catastrophic consequences for our reading of the cosmic story. A slight over-subtraction of galactic dust could artificially create the faint, curling pattern of primordial gravitational waves, the very beam modes we are desperately searching for. Conversely, an under-subtraction could completely hide that signal forever, leaving us blind to the universe's first tremors. This constant, painstaking battle against foreground contamination is a monumental source of uncertainty in modern cosmology. It is also a powerful engine for innovation, driving the development of exquisitely sensitive detectors and telescopes that can scan the sky across an ever wider range of frequencies. The quest to see the true face of the early universe forces us, ironically, to become world experts on the detailed physics of our own galactic home, ensuring that every new map of the cosmos is also a deeper portrait of the Milky Way. So we are left with a map of the infant universe that is almost too perfect, yet scarred by a handful of strange, persistent imperfections. The axis of evil, the cold spot, the curiously faint quadrupole, and a handful of other, smaller anomalies all stand in defiance of our beautiful, simple standard model. Each one on its own could be a crack in the foundation of modern cosmology, a whisper of new physics, but collectively they present scientists with a profound and deeply human dilemma, the agony of the look elsewhere effect. This is the statistical reality that if you scrutinize any large and complex dataset with enough intensity, you are almost guaranteed to find patterns that appear wildly improbable. It is the cosmic equivalent of seeing a face in the clouds. The universe is vast, and the cosmic microwave background map contains a staggering amount of information. If you search through enough angles, enough scales, and enough statistical measures, something, somewhere, is bound to look strange just by pure random chance. The question is, which of these anomalies are genuine faces and which are just fleeting clouds? For the researchers who dedicate their lives to these puzzles, this is a professional high-wire act. To chase an anomaly is to gamble years of one's career on the possibility that a statistical fluke is actually a fundamental discovery. It requires a delicate balance of stubborn conviction and rigorous self-doubt. The standard cosmological model, lambda CDM, is a towering achievement. It predicts the vast majority of what we see with breathtaking accuracy. To suggest it is wrong based on a few shaky outliers requires immense courage. Yet history tells us that sometimes the outliers are the key to the next great leap. The entire field of cosmology now lives in a state of perpetual suspense, a community holding its breath. New telescope data is analyzed not just to confirm what we already know, but to see if one of these ghosts in the data will finally step into the light as a concrete discovery or fade away into statistical noise. This tension is the engine of science itself, the thrilling, maddening struggle to distinguish between a mirage and a new continent on the map of reality. There is a final, humbling frontier in our study of this ancient light, a boundary not of technology but of physics itself. The cosmic microwave background is not a three-dimensional volume we can explore. It is a two-dimensional surface, a shell at the edge of the observable universe known as the last scattering surface. every photon we detect has traveled in a straight line from that single, thin layer where the universe first became transparent. We are essentially looking at the cosmic fireball's glowing skin. This creates a profound informational limit. We cannot see behind this surface. The universe before 380,000 years of age is permanently shrouded, hidden behind a brilliant wall of light. It is like trying to understand the core of the Earth by only studying its surface crust. The violent, inflationary epoch that set everything in motion happened long before this surface formed, and its direct details are forever lost to that opaque veil. Our vision of the beginning is fundamentally indirect, pieced together from echoes. Compounding this limitation is a statistical ghost known as cosmic variance. On the very largest scales, the scale of the entire observable universe, we face a simple, frustrating truth. We only have one universe to measure. Think of it like trying to understand the average height of all humans by only ever meeting one single person. Any measurement you take from that one individual might not be representative of the whole population. In cosmology, the largest patterns in the CMB, like the faint quadrupole or the axis of evil, are unique events. We have only one sample of them. We cannot know if the strange quiet we observe on the grandest scales is a genuine feature of the cosmos, or just a statistical fluke of our particular cosmic neighborhood. This cosmic variance sets a fundamental ceiling on the precision of our knowledge. It means some of the most profound questions we have about the very first moments, the true nature of the Inflaton field, or the ultimate geometry of everything, might be permanently unanswerable by studying the CMB alone. This realization is not an end, but a new beginning. It pushes cosmology forward, forcing scientists to devise new ways to peer deeper into the darkness. The hunt is now on for even more primordial signals, like the faint radio whisper of 21-centimeter radiation from the cosmic dark ages, the era before the first stars ignited. Or the dream of detecting a stochastic gravitational wave background, a permanent hum in spacetime from the violent birth of the universe itself. These are the new messengers, carrying information from a time before the first light was ever set free. This ancient light is not just a simple temperature map. It is also polarized, a subtle property that tells us the direction in which its waves are vibrating. Within this polarization lie two distinct patterns known as E modes and B modes. Think of them as two different kinds of wrinkles on the surface of a pond. E modes are the simple, radial patterns, like the ripples that spread out from a single dropped pebble. These are generated by the density fluctuations in the primordial plasma, the same seeds that grew into galaxies. They are a curl-free pattern, confirming the story we already read in the temperature map. B modes, however, are far more elusive. They are the swirling, curling patterns in the water, like tiny vortices. These can be created by two very different cosmic phenomena. The first and most famous are the primordial gravitational waves from inflation, the holy grail of cosmology. But the second source is gravitational lensing. As the CMB light travels for billions of years across the universe, the gravity from all the dark matter and galaxies it passes warps its path, subtly twisting the E-mode polarization and converting a small fraction of it into a lensing-induced B-mode signal. This secondary B-mode is not a disappointment. It is a powerful tool in its own right. By mapping these lensing B-modes, scientists can actually chart the distribution of all the matter, including the dark matter, throughout cosmic history. It is like using the distorted light from the cosmic fireball to create a three-dimensional mass map of the entire universe. This polarization data provides an independent and incredibly clean check on our cosmic parameters. While the temperature map can be muddied by foreground dust and gas, the polarization signals offer a clearer view, a second witness to the events of the early universe. The relentless, precise measurement of these faint patterns is not just a technical exercise. It is how we cross-examine the cosmos, ensuring the story told by the temperature of the ancient light is the same one whispered by its polarized echo. Billions of these ghost particles streamed through the searing plasma of the infant universe, a silent wind blowing through the newborn cosmos. These are neutrinos, and while they barely interact with matter, their collective presence left a subtle fingerprint on the cosmic microwave background that we can still read today. In those first moments, the universe was so dense that even these phantom particles were trapped, bouncing and colliding in the hot soup. But around 1 second after the Big Bang, as the cosmos expanded and cooled, something pivotal happened. Neutrinos broke free. They began streaming across the universe almost completely unimpeded, a vast, invisible sea. This great neutrino exodus had a profound effect on the primordial plasma left behind. The gravity of these streaming neutrinos subtly tugged on the clumps of matter and energy, smoothing them out and suppressing the growth of the very smallest ripples. Imagine a pot of thick soup just beginning to simmer with tiny bubbles forming. Now picture a gentle, steady wind blowing across its surface. That wind would prevent the tiniest bubbles from ever fully developing, while allowing the larger ones to persist. This is the neutrino drag effect, a damping of the small-scale anisotropies in the CMB. The precise pattern of hot and cold spots we observe is not just a record of density variations, but a fossil of this ghostly particle wind. By measuring the exact amount of this damping, scientists can perform an incredible feat, weighing the neutrino. Current data from the CMB tells us that the combined mass of all 3 known types of neutrinos is astonishingly small, a minuscule fraction of the mass of a single electron. This ancient light provides the most stringent limits we have, confirming that these phantoms are almost but not quite weightless, yet the mystery deepens. We know neutrinos have mass, but we do not know the exact values for each type or what their mass hierarchy is, which one is the heaviest and which is the lightest. Future generations of CMB observatories are being designed with one explicit goal: to detect the subtle signature of neutrino drag directly. Successfully measuring this effect would be a monumental achievement, a direct window into physics at the very edge of the standard model of particle physics. It would tell us not just about the universe's first second, but about the fundamental building blocks of reality itself, revealing how the ghostly whispers of the past sculpted the cosmic structures of the present. Our universe might be sewn together with cosmic threads. Beyond the dominant theory of inflation lies a wilder, more tangled possibility: the existence of topological defects. These are not objects in space, but cracks in the very fabric of spacetime itself, relics of a time when the fundamental forces of nature were undergoing a dramatic separation. Think of it like this: when water freezes into ice, the transition is not always perfectly smooth. Defects can form, tiny cracks and boundaries between different crystal domains. In the same way, as the searing hot early universe expanded and cooled, the underlying fields that govern reality underwent similar phase transitions. If this transition happened in a chaotic, lopsided way, it could have frozen imperfections into the structure of spacetime. These defects come in different, mind-bending forms. There could be cosmic strings, unimaginably thin, one-dimensional filaments of pure energy, thinner than an atom but stretching across the cosmos, with the mass of a mountain range packed into every inch. A single string vibrating through space would warp the fabric of reality around it, creating a gravitational lens that could duplicate the image of a distant galaxy. Then there are domain walls, two-dimensional sheets that would act as impenetrable barriers, separating regions of space with different properties. and textures which are more like knots in the fields of spacetime that could suddenly unravel, releasing a burst of energy. Each of these defects would have left a unique and powerful signature on the cosmic microwave background. A network of cosmic strings, for instance, would have created sharp, linear steps in the temperature map, like scratches on a photographic negative. Yet, when we look at the exquisitely detailed Planck data, we see a sky that is overwhelmingly smooth. The patterns of hot and cold spots align beautifully with the predictions of inflation, not with the jagged scars of topological defects. The current evidence strongly suggests our universe had a very clean, orderly birth, one smoothed by that violent inflationary spurt. So, does this mean the wilder theories are dead? Not entirely. The fact that we have not found these defects is itself a profound discovery. It places incredibly stringent limits on the kinds of phase transitions that could have occurred, effectively ruling out whole families of theoretical models for how the fundamental forces split apart. This absence is a silent message from the dawn of time, telling us something about the symmetry of the infant cosmos, but a small, dedicated community of physicists remains on the hunt. They scrutinize the CMB data for any anomalous, sharp feature that the smooth inflationary model cannot explain. They search for the telltale gravitational wave background that a network of cosmic strings would produce. They are looking for the ghost in the noise, the one crack in a seemingly perfect facade that could reveal a much more complex and twisted story of creation, a universe not just inflated, but stitched together with cosmic seams. That first light traveled for almost 500,000 years through a universe growing cold and dark. After the cosmic microwave background was released, the cosmos entered its cosmic dark ages, a time devoid of stars, filled only with vast clouds of neutral hydrogen and helium gas. This profound silence would not last. A few 100,000,000 years later, a new light began to dawn. The first stars and galaxies ignited, and their furious ultraviolet radiation began to tear electrons from those neutral atoms, starting a process known as re-ionization. The universe was being fundamentally transformed, and this great upheaval left its own subtle mark on the ancient light. As the CMB photons continued their endless journey, some of them passed through these newly ionized regions. The free electrons there scattered the photons one last time, imprinting a distinct, large-scale pattern of polarization onto the primordial signal. This is not the curling beam mode from inflation, but a broader, more diffuse pattern that acts as a fossil record of this cosmic renaissance. By meticulously measuring this polarization, cosmologists can perform a remarkable kind of cosmic archaeology, using the CMB as a backlight to trace the history of re-ionization itself. They can determine when it started, how long it lasted, and perhaps even how it unfolded. Was it a swift and violent transition, driven by an early population of incredibly massive, brilliant stars that flooded the cosmos with ionizing radiation in a relatively short burst? Or was it a more gradual and drawn-out affair, with smaller galaxies slowly eating away at the neutral hydrogen over a much longer period? The current data from the Planck satellite suggests re-ionization was roughly halfway complete by the time the universe was around 550 million years old. But the full story remains frustratingly murky. Pinpointing the exact timeline is one of the most critical challenges in cosmology, because this epoch is the essential bridge. It connects the smooth, simple universe revealed by the CMB to the complex, structured universe of galaxies we see around us today. Without re-ionization, the cosmos would have remained an opaque fog, and the light from all subsequent stars and galaxies would be hidden from our view. This ancient polarization signal is therefore more than just a data point. It is a direct probe into one of the most transformative and mysterious chapters in cosmic history, a time when the first structures lit the fuse for everything that was to come. Even our own motion through the cosmos is written in this ancient light. The cosmic microwave background is not perfectly uniform in every direction. It carries a dominant, fundamental pattern known as the dipole anisotropy. In one direction of the sky, the CMB appears very slightly warmer, while in the exact opposite direction, it appears correspondingly cooler. The standard explanation for this is a familiar cosmic version of a common earthly experience, the Doppler effect. Just as the pitch of a siren rises as an ambulance races toward you and falls as it moves away, the light from the CMB is blue-shifted to a slightly higher energy, and thus a slightly warmer temperature in the direction we are moving. In the direction we are fleeing, the light is redshifted, appearing cooler. This measurement tells us that our entire solar system is hurtling through space at a staggering 630,000 kilometers per hour relative to the primordial rest frame of the universe itself. This is our true cosmic velocity, measured against the most fundamental backdrop imaginable. It serves as the ultimate anchor, the primary reference frame for the entire cosmos, against which all other motions are measured. Yet, some scientists peer at this most basic of signals and ask a dangerous question. Is it all just motion? Could a tiny, stubborn fraction of that temperature difference be not from our local journey, but a genuine feature imprinted on the universe at its birth? The consequences of such a discovery would be dramatic. A primordial dipole would suggest that the universe itself might have a preferred direction on its largest scales from the very beginning, a fundamental lopsidedness that would shatter the cosmological principle to its core. While the evidence overwhelmingly points to our motion as the cause, the mere possibility forces a profound humility. It reminds every cosmologist that even the most settled, simplest interpretations must be held lightly, subject to relentless scrutiny. If an anomaly were ever confirmed in this most basic feature, it would send shockwaves through the entire field, proving that the oldest light still has the power to unsettle our most fundamental assumptions about the cosmos. Hidden within the apparent randomness of the hot and cold spots is a deeper statistical secret, a clue to the very nature of the universe's violent birth. The simplest models of inflation predict that these primordial fluctuations should be Gaussian. This is a statistical term for a very specific kind of randomness, the kind you see in a classic bell curve. Most of the fluctuations would be small and average, with a few larger hot and cold spots appearing just as often as one another, scattered purely by chance. It is the cosmic equivalent of the static on an old television, a fundamentally random hiss with no hidden patterns. But what if the static is not completely random? Many alternative theories of the early universe, particularly those involving multiple Inflaton fields interacting in a complex cosmic dance, predict something different. They forecast a detectable level of non-Gaussianity. This means the statistics of the CMB map would show subtle correlations, a faint but distinct signature of interaction. It would be as if, within the television static, you could occasionally make out the ghostly, overlapping outlines of faces. These would not be faces, of course, but a specific statistical skewness, a telltale sign that the seeds of creation were sown by a more intricate process than a single, simple field. A clear detection of this non-Gaussian pattern would be a monumental discovery. It would immediately rule out the most basic and elegant versions of inflation, forcing us to embrace a messier, more complex Genesis story, perhaps one involving multiple fields or even a bouncing universe that existed before the Big Bang. The fact that our most precise maps, like those from the Planck satellite, have found no significant non-Gaussianity is a powerful victory for the standard inflationary picture. Yet the hunt is far from over. scientists continue to develop ever more sophisticated statistical tools, combing through the cosmic data for any faint, anomalous correlation. They are searching for a ghost in the static, a whisper of a more complicated truth, knowing that its discovery would tear down our simplest story of creation and force us to build a new, more wondrous one in its place. This ancient light does more than just tell a story of our past. It actively tests the most fundamental laws of nature, the extreme conditions of the universe's first moments, preserved in the cosmic microwave background, create a unique laboratory for physics. Here we can probe ideas that are utterly untestable here on Earth. Consider the quest for a theory of quantum gravity, the holy grail of modern physics. This is the effort to unify Einstein's general relativity, which governs the very large, with quantum mechanics, which rules the very small. The violent, subatomic scale universe during inflation is the one place where these two titanic theories must have met and interacted. That interaction could have left a faint, telltale scar on the patterns of the CMB, a specific twist in the polarization that our telescopes are now hunting. Similarly, the CMB can test whether the fundamental constants of nature are truly constant. What if the fine structure constant, which sets the strength of electromagnetism, was slightly different in the early universe? Even a minuscule variation would have altered the way light and matter interacted in that primordial plasma, shifting the precise sizes and proportions of the hot and cold spots we observe. Our exquisitely detailed maps of the CMB allow us to check for this, effectively using the cosmos as a time machine to measure the laws of physics billions of years ago. Another profound possibility is a violation of Lorentz invariance, a cornerstone of Einstein's relativity, which states that the laws of physics are the same for all observers, regardless of their direction or speed. If this principle were broken in the extreme environment of the early universe, it would have imprinted a specific directional pattern, an asymmetry, on the CMB. By searching for these ghosts of exotic physics, cosmologists are placing incredibly tight constraints on theories that operate at energy scales 1 trillion times higher than anything we can create at the Large Hadron Collider. The cosmic microwave background is no longer just a fossil to be studied. It has become an active, cosmic-scale testing ground. Every new, more precise measurement tightens the leash on these wild ideas, either ruling them out or, perhaps one day, revealing a crack in our current understanding that leads to a new revolution in physics. The Planck satellite mapped the cosmos with breathtaking detail, but its legacy is not an ending. It is a starting pistol for a new generation of observatories, both on the ground and in space, designed to listen to the ancient light with a sensitivity we once thought impossible. These are not merely incremental upgrades. Projects like the Simons Observatory in Chile and the even more ambitious CMB S4 represent a quantum leap in our ability to see. They will deploy not hundreds, but hundreds of thousands of superconducting detectors across their telescope arrays, creating a collective eye on the sky of staggering power. Their primary mission is to hunt for the faintest whispers in the CMB's polarization, the elusive curling pattern of primordial gravitational waves. With this new level of precision, they aim to either finally capture that foundational signal or rule out entire classes of inflationary models, forcing a dramatic rethink of the universe's first moment. But the ambition does not stop there. This flood of new data will also allow scientists to perform a feat that sounds like pure magic, weighing the neutrino. By measuring the subtle damping effect that a sea of streaming neutrinos had on the smallest ripples in the CMB, these observatories could pin down the total mass of these ghostly particles, a fundamental question that has eluded particle physicists for decades. Every anomaly we have encountered, from the axis of evil to the cold spot, will be scrutinized with a magnifying glass of unimaginable power. Is the faint quadrupole a statistical fluke or a genuine feature of a finite cosmos? Is there a hidden non-Gaussianity in the static, a sign of a more complex genesis? The future of CMB science is a high-stakes interrogation of reality itself. These next-generation experiments promise to either solidify our standard model of cosmology into an unshakable edifice, or reveal the cracks that will force the next great theoretical leap, proving that the oldest light in the universe still has profound secrets left to tell. Our entire cosmic history is written on a single, spherical shell of light. This last scattering surface is the ultimate horizon, the final frontier from which any signal can ever reach us. Every galaxy, every star, every piece of data we have ever collected about the cosmos comes from within this bubble, but what lies beyond its glowing edge? The answer is a profound and humbling silence. We are forever trapped inside a cosmic fishbowl, building our grand theories of the universe from a finite and possibly completely atypical sample of reality. This is the philosophical chasm the cosmic microwave background opens before us. We assume the laws of physics are the same everywhere, that our little patch is a fair representation of the whole. But what if it is not? What if the universe beyond our horizon is utterly alien, with different constants, different dimensions, or even different fundamental forces? The cosmic microwave background gives us no way to know. It forces us to ask whether the concept of the universe has any real meaning beyond what we can observe. Are we like a deep-sea creature that has never broken the surface, trying to understand the concept of air, of continents, of a sky filled with stars, based solely on the murky water it has always known? This ancient light is therefore more than a physical boundary. It is a limit on knowledge itself. It tells us that some questions may be fundamentally unanswerable, that our grandest cosmological models are, at their heart, a description of our local neighborhood within an immeasurable vastness. We are left to wonder if we are mapping a single room, while the true mansion of reality stretches into an infinite, unseen darkness. The smooth, orderly universe we observe might be a local artifact, a single bubble in a frothing cosmic sea. This breathtaking idea emerges when we push the theory of inflation to its logical extreme and marry it with string theory, a candidate for a theory of everything. In this framework, the vacuum energy that drove inflation is not a unique value but can take on a vast number of possible states, a theoretical landscape of unimaginable complexity. Our entire cosmos, then, could be just one pocket where the Inflaton field settled into a particular valley, giving us our specific laws of physics and constants. But in this eternal, meta-stable foam, countless other bubbles could be nucleating, expanding, and cooling, each with its own completely different reality. Some might have stronger gravity, rendering stars impossibly short-lived. Others might have no electromagnetism, and thus no light or chemistry as we know it. This is the string theory landscape, a multiverse of potentially infinite variety. While this concept seems permanently beyond our direct view, the cosmic microwave background provides one of the only conceivable observational windows. A collision between our expanding bubble and a neighboring one in that primordial foam would have been a cataclysmic event, releasing an immense amount of energy. Such a collision could have left a permanent, cooler bruise on the skin of our cosmos, an imprint that some scientists speculate we might already have seen in the form of the mysterious cold spot. Furthermore, the very statistical properties of the fluctuations we see in the CMB, the specific pattern of hot and cold spots, could in principle carry a faint signature of our bubble's specific place in the wider multiversal landscape. It is a long shot, a whisper of a whisper, but it means that the map on our screens is not just a picture of our beginning. It could be a census report from a much larger reality, placing this ancient light at the heart of the most profound question we can ask. Are we alone in existence, or is our universe just one page in an infinite cosmic library? This ancient light offers something almost unique in all of science, a tangible connection to the absolute beginning. It is not a theoretical abstraction or a fleeting signal, but a permanent, measurable presence, a data set of breathtaking precision that somehow remains endlessly interpretable. The cosmic microwave background provides the unshakable foundation for our standard model of cosmology, a structure so robust it can predict the universe's composition and history with stunning accuracy. Yet, carved into that very foundation are those stubborn anomalies, the axis of evil, the cold spot, the faint quadrupole, cracks that refuse to be sealed by better data or more sophisticated models. For the scientists who study it, the CMB is the ultimate archaeological find, a perfectly preserved cosmic scroll from the dawn of time. The problem is, we are still learning how to read its language. Every translation, every deciphered line, seems to reveal a deeper layer of poetry and paradox. A solved mystery does not bring closure, but instead unlocks two new, more profound questions. This is the source of its enduring allure, the restless, obsessive drive that fuels a lifetime of research. It is the agonizing and thrilling position of knowing you have the right map in your hands, while simultaneously seeing faint, tantalizing traces of undiscovered continents drawn in its margins. This combination of solid ground and infinite mystery is what truly keeps cosmologists staring at the day till late into the night, forever wondering what the next whisper from the dawn of time will reveal. From its faint, uniform glow to its intricate tapestry of anisotropies, the cosmic microwave background stands as our most valuable and vexing relic. This ancient light has guided us through a landscape of profound mysteries, from the horizon problem that demanded a violent cosmic inflation to the haunting Hubble tension that pits the early universe against the modern one. It has presented us with a map that is at once stunningly precise and strangely flawed, marked by a possible axis of evil and enigmatic cold spots. With every answer it provides, this primordial whisper seems to generate two deeper, more challenging questions. The universe feels no obligation to make itself easily understood by human minds. It operates on scales and by rules that can stretch our intuition to the breaking point. And that is precisely what makes this pursuit so electrifying. As we construct ever more sensitive telescopes and deploy vast arrays of detectors across remote deserts and polar ice, we are not just finishing a story. We are opening a new chapter, listening with bated breath for the next whisper hidden within the patterns. The next great revolution in physics is likely encoded in that faint, cosmic static, waiting for the moment we finally learn how to hear it. Which of these cosmic mysteries keeps you awake at night? Let us know in the comments, and be sure to subscribe for more journeys to the edge of our understanding.